Bismillahirrahmanirrahim. Dear students, in this week we will solve another problem related to shear force diagram and bending moment diagram. So let's read the statement of the problem. It says that the footing supports the loads transmitted by the two columns. So this part is a footing and it is supporting two columns. The load transferred to the footing by each column is equal to 60 kilonewton as it is marked on the diagram. Further, the problem statement says that draw the shear and moment diagrams for the footing if the reaction of soil pressure on the footing is assumed to be uniform. So we are assuming that these 2 point loads are generating uniform pressure under the footing. So we will have to calculate how much is that pressure, and then considering that pressure as well as these 2 point loads, we will draw the shear force diagram and bending moment diagram. Now you may think that in this problem it's given that the pressure is uniform. So can there be cases when the pressure will not be uniform under the footing? So the answer is yes, that there might be cases when the pressure under the footing might not be uniform, and those cases appear when the loading is unsymmetrical. By unsymmetrical I mean either the magnitude of loads are not equal to each other, or they are not at equal distance from the centroid of the footing, etc. When you will study the problems related to columns and related to combined stresses, you will learn that how to deal with such situations. However, in the problems related to shear force diagram and bending moment diagram, we will remain ourselves limited to such cases when the pressure is uniform underneath the footing. Okay, so let's draw the free body diagram. So this is the free body diagram of the given problem. This dotted part is showing the footing, and then we have 60 kilonewton load, first load, which is transferred from this column acting at 2 meter distance from the left edge of the footing, and then we have another 60 kilonewton load which is transferred by the other footing, and the uniformly distributed reaction that is supposed to be generated under the footing is marked on this diagram. Now as we know that the situation is symmetrical and the pressure is uniform, so it is very easy to calculate the intensity of this pressure. Omega is the intensity. The total magnitude of load acting in the downward direction is 60 plus 60 equal to 120, and that is divided over the entire length of the footing. So 120 divided by 8, this 8 is the length of the footing. It gives us 15 kilonewton per meter. So in this way we have calculated the intensity of the force or the magnitude of the UDL acting at the bottom of the footing. Now this problem is slightly different than the problems that we solved earlier. Probably before this we did not solve any problem that has forces acting in the upward direction, and plus in this case we have sort of overhang in both the directions. You can consider these forces like 60 kilonewton and 60 kilonewton, though point loads, you can assume them to be support reactions, and then we have overhanging part on both the sides. And in future when you will be doing some foundation design, you will incorporate such situation. So this concept is important to understand at this point. Now according to our convention on which we divide the beam into portions, we consider the dividing line of the portions whenever we see any change in loading or change in support condition. There are no hinge or roller supports present here, so we will just look at the change in the applied loading. So if we start from left end, we start from this end and we start moving in the rightward direction, the first change in loading or the abrupt change in loading is observed at this point. So we can label it as point B. So portion AB will our first portion, and then if we further move in the rightward direction, we see another point load at point C. So portion BC will be our second portion, and then if we start from this point C and move in the rightward direction, the beam terminates at point D. So portion CD will be our third portion. Here I have written all these three portions, AB, BC and CD. So now we will consider these portions one by one, and we will draw the free body diagram. We will write down the equation of shear and bending moment, and we will calculate the magnitude of shear and bending moment for all the terminal points of the portions. So let's consider portion AB first. Portion AB is this part, like right before the 60 kilonewton load. So here is the free body diagram of portion AB. The range of X is from 0 to 2 meters. So it starts from here and it goes up to this point. And this is the UDL. It's acting in the upward direction. Intensity is 15 kilonewton per meter. We do not know its exact length because the section varies from 0 to 2 meters. So this distance is X. Now, whatever portion of UDL is present on the left side of the section, the centroid will be acting at the mid of that portion. So if this total length is X, then the centroid will act at X by 2. And V is the exposed shear and M is the exposed bending moment. So this completes the free body diagram of this problem. Now let's apply the conditions of equilibrium to get the equations of bending moment and shear force. Sigma Fy equal to 0 with the convention that positive forces will be treated as, like upward forces will be treated as positive. 15 is the intensity of this UDL and X is the span over which it is acting. So 15X is the resultant of the UDL, which is marked with a dotted arrow here, and it is acting in upward direction, so it is positive. And then this exposed shear V is acting in downward direction, and this is equal to 0. If we rearrange this equation, we get V is equal to 15X, and the presence of X in this equation indicates that the shear force is varying along this portion. So as X changes, the magnitude of shear force will also change. So for both the terminal points, starting and ending point of this portion, we will calculate the value of shear. So at point A, X is equal to 0 because X is starting at A, and VA will be equal to 15 times 0 equal to 0. And at B, X is equal to 2 meters. B is the end point of this section here, and X is equal to 2 meter. So when we will plug in V, we will get the value of VB. 15 into 2 equal to 30 kilonewton, and this is positive. So at point A, shear force is 0, and at point B, shear force is 30 kilonewton. Now is this 0 logical? This is free end of the beam or the footing, and there is no point load acting at this free end. So having 0 shear is totally logical for this case. Okay, and then sigma mx equal to 0. Our convention will be clockwise movement will be taken as positive. 15 into x by 2. This is basically the movement caused by the resultant of this UDL. 15 into x is the magnitude of the resultant, which is acting in the upward direction, and about the section it will produce movement in counterclockwise direction. Although we have solved a lot of problems, but I see that some of the students are still confused about the movement center, and they assume that we are calculating movement about some support or about the starting point of the portion. So that's not the case. We always calculate movement about the section. So 15 into x, this is the magnitude of the resultant, and x by 2 is the perpendicular distance between this resultant and the section under consideration. So 15 into x by 2, and this will produce movement in clockwise direction, so it should be taken as positive. And then this exposed movement that is acting in counterclockwise direction, so it should be taken as negative, and this is equal to 0. So m is equal to 7.5 x square. This is the value of the equation of bending moment for portion AB. And again, the presence of x indicates that bending moment changes throughout the length of the beam, throughout the length of this portion AB. So we'll plug in the values of x for point A and point B, and we will get the values of movement at these 2 points. So at A, x is equal to 0 and MA comes out to be 0. Now is this 0 logical? Point A is free end of this beam, and there is no point moment acting at point A, which means that the bending moment at point A should be equal to 0. So this 0 is totally logical. And then at point B, x is equal to 2 meters, mb is equal to 7.5 into 2 square, and that comes out to be 30 kilonewton meter. So we have got the values of moment for point A and point B. Now let's move to the next portion. Next portion is portion BC. So if I cut a section here and I want to consider the entire left part of the beam, then I will have this UDL up to the section and this point load 60 kilonewton acting at point B. So let's see how this free body diagram looks like. So we have this free body diagram. This is point A, point B, and the section is cut somewhere after point B. The UDL intensity is the same throughout the length, so intensity is 15 kilonewton per meter, and we have a force, point load, acting in the downward direction at point B with a magnitude of 60 kilonewton. The length of this portion is x, and the part of the beam present on the left side of this point load is 2 meters. So how much will be this perpendicular distance between the section and the applied load? It will be x by 2. And how much will be the magnitude of the resultant in this case? 15 is the intensity and x is the distance over which it is acting. So again, r will be equal to 15 into x, and the lever arm of 15 into x resultant will be equal to x by 2, because this part which is present, this part of the UDL present under the beam, the total span is x, so the resultant will act at a distance x by 2 from the section. So this completes the free body diagram for this portion. And yes, the last thing is the exposed shear and exposed bending moment. Now we are in a position to write down the equations of shear force and bending moment. Sigma Fy equal to 0 with upward forces acting with upward forces as positive. So 15 into x. It is the resultant of this UDL, 15 into x, as it is acting in upward direction, so it will be taken as positive. And then minus 60, which is acting in the downward direction, and this exposed shear, which is also acting in the downward direction, so with a negative sign. If we rearrange this equation, we get V is equal to 15x minus 60. And we have got the equation. X is present in the equation, which indicates that shear force is varying along the length of the portion. So we will plug in the values of the two extreme points of this portion and the value of x, and then we will get the value of shear force for these 2 points. So at B, x is equal to 2 meters, and we'll put it in the equation of shear, and we'll get the value of shear for VB for point B, and it comes out to be minus 30 kilonewton. Similarly, for point C, we will plug in the value in the same equation. Value of x is 6 meters, so VC turns out to be 30 kilonewton. You can see that the signs are different. So this minus 30 will be plotted on the downward side of the 0, 0 line, and this plus 30 will be plotted on the upward side of the reference axis. Now let's write down the equation of bending moment. For that, again, we will calculate the bending moment at the section, like about the section. So 15 into x is the magnitude of the resultant of this UDL, and it will produce moment in clockwise direction. So 15 into x, and the lever arm, as we earlier discussed, is equal to x by 2. 15 into x by 2. And then the 60 kilonewton force, it is producing moment in counterclockwise direction. So minus 60 into x by 2, sorry, x minus 2. As we discussed earlier, that the part of the beam present on the left side of this force is 2 meters, total is x, so this part is x by 2. And last thing is this exposed moment, which is in counterclockwise direction, so minus m is equal to 0. And if we rearrange this equation, we get m is equal to 7.5 x square minus 60x plus 120. Again, we have variable x present in this equation, which means the moment is varying along the span BC. So we need to calculate the value of moment for point B as well as point C. at B, x is equal to 2 meters. So MB, when we put x equal to 2 meter in this equation, MB turns out to be 30 kilonewton meter, and this is positive. For point C, x is equal to 6 meter, MC is equal to 7.5 into 6 square minus 60 into 6 plus 120, and we get 30 kilonewton meter. Now in this case we are getting same value of bending moment for both the points. When we will plot the bending moment diagram, we will see that how to deal with this situation, whether these 2 points should be joined just directly or we need to make any change. We will see that when we will be plotting the bending moment diagram. So this completes our discussion about the second portion BC. Now let's move towards the third portion CD. If we look at the total beam, portion CD is here. If we cut a section here and we consider the entire part of the beam that is present on the left side, we have this UDL up to the section, and we have 2 point loads, one acting at point B and the other acting at point C. So we will consider all these loads while drawing the free body diagram of portion CD. So let's see how this free body diagram looks like. So we have this beam, this is the section passing through portion CD. This is 60 kilonewton first load acting at point B. This is 60 kilonewton force acting at point C. The X is starting from point A. So the portion of UDL which is present up to the section has length X. Resultant of this portion will pass through the center. So location of the resultant will be X by 2. And what about the distance between the 60 kilonewton force and the location of resultant? The part of the beam present on the left side of the beam is force is 2 meters. Total length is X. So this distance present between this 60 kilonewton load and the section is X minus 2. And for this 60 kilonewton force, the part of the beam present on the left side of the force is 6 meters, 2 plus 4. So the distance, perpendicular distance between this load and the section is X minus 6. And the last thing is the exposed shear force and bending moment. This completes the free body diagram for portion CD. Now let's write down the equations of shear and bending moment. For shear, we will apply sigma Fy equal to 0 with upward forces considered as positive. 15 into X, what is that? This is the magnitude of the resultant of this UDL as it is acting in upward direction. So this is positive, 15 into X. Then this minus 60 kilonewton force acting in the downward direction and minus 60 kilonewton load acting in the downward direction further. And at the end we have this shear force V acting in the downward direction. And if we rearrange the equation, we get V is equal to 15x minus 120. X is present in this equation, meaning that we will have to calculate the shear force for point C and point D separately. So in this equation for point C, if we put X equal to 6 meter, we get VC equal to minus 30 kilonewton. And at point D, X is equal to 8 meter. So if in the equation of shear we put X equal to 8 meter, we get VD equal to 0. Now is this 0 logical or not? What do we have at point D? Let's go back to our main figure. Point D is a free end, and at point D there is no point load acting. So we know that at free end, if no point load is acting, the magnitude of shear should be equal to 0, which indicates that this zero value of shear, this zero value of shear for point D is totally logical. Now next part is to write down the equation of bending moment for portion for this portion CD. We'll apply sigma mx equal to 0 and we'll take clockwise movement as positive. First is this UDL, 15 kilonewton force, 15 kilonewton per meter acting over a span of x. So 15 into x is the magnitude of the resultant, and its perpendicular distance with respect to section is x by 2 as it is labeled here. and this resultant will produce moment in clockwise direction, so it should be taken as positive. 15 into x by 2 is the moment generated by this force about the section. Then the next force is the 60 kilonewton force. It is producing moment in counterclockwise direction, so it will be taken as negative. Minus 60 into x minus 2. X minus 2 is this distance from 60 kilonewton force up to the section. And then this last 60 kilonewton force, which is also producing moment in counterclockwise direction, so it should be taken as negative. And the lever arm is x minus 6, and lastly this exposed moment m. So m, and we'll put it equal to 0. Now if we just solve all these terms and we simplify the relationship, we get m is equal to 7.5x square minus 120x plus 480. And as it's a second degree equation, x is present, so we will calculate the value of bending moment for points C and D separately. At C, x is equal to 6 meter. So MC, when x equal to 6 meter is put in this equation, we get MC equal to 30 kilonewton meter. And at point D, when we put x equal to 8 meters, MD comes out to be 0. Is this 0 logical? Let's go back to our main diagram. At point D, we have free end, and there is no point moment acting at point D, which means that the value of bending moment should be equal to 0 at point D. So this 0 is totally correct. Sorry, not this 0, rather this 0. It's free end. So now we have calculated the values of shear and bending moment for all the important points of this beam, and we are in a position that we can start drawing shear force diagram and bending moment diagram. So here are these diagrams. First of all, we need to draw the free body diagram of the beam. We have a UDL acting in upward direction, 15 kilonewton per meter. These two 60 kilonewton forces are also marked. All the distances are marked on the diagram. We will draw the reference lines wherever we see a point on like a label on the beam A, B, C, D. Against every point we will draw a reference line. And then the plotting of shear force diagram, it's merely plotting of those values that we have already obtained. If you go back at point A, the value of shear is 0. At point B, it is equal to positive 30 kilonewton, and at point B, the next value, like for point C, we have two values. First value is coming from, at point B, the first value is coming from portion AB. So where is portion AB? The value of shear for point B from AB side is 30 kilonewton positive, and the value of shear for the same point from portion BC is minus 30 kilonewton. So here on the free body on the bending shear force diagram, the first ordinate is 30 and the next ordinate is minus 30, and these will be joined with a straight line because the equation representing the variation of shear for portion AB is a first degree equation. Then portion BC, one value is negative 30. At point C, the value is positive 30, and the equation is first degree, so we will join these 2 points with a straight line. And then the value of shear for point C from portion CD side is minus 30, and the value of shear at point D is 0. So we will join these 2 points together, and this is a straight line because the equation of shear for portion CD is a first degree equation. Now our shear force diagram is closing. I have discussed this thing earlier, that by closing of shear force diagram, I mean that the value of shear at this extreme point will be either equal to 0 or it will be equal to any point force acting at this point. It may be a reaction or it may be action. That does not matter. Okay, so in this case the value of shear at point D is 0. It's a free end, there is no point load acting, so that's totally fine. Shear force diagram is closing, and this indicates that our calculations at this stage are correct. Next step is to draw the bending moment diagram. For bending moment diagram, at point A, value of bending moment is 0. We have already calculated that. At point B, it is equal to 30. Let me just go back to the equation of bending moment for portion AB. If you look at this equation, this is the equation of bending moment for portion AB, this portion AB. So it's 7.5 x square. The degree of the equation is second. It means that these 2 points that we have marked on the bending moment diagram, we cannot join them with a first degree line, not with a straight line. So these 2 points, now one thing we know that will be joined with a second degree line. Now next question is whether second degree line will be convex up or concave up. For that, we will have to look at the magnitude of the shear force. As the magnitude of the shear force is increasing, so the slope of bending moment diagram should also be increasing. Now if we draw a tangent to this point of the bending moment diagram, its slope is 0. And if we draw a tangent at this point of bending moment diagram, it has some value of slope, which indicates that the slope is increasing as we are moving in the rightward direction. So this is how we decide that what should be the orientation of this curve. And we have discussed this thing several times, and I have posted a separate FAQ video in probably fourth week lecture videos as well. So if you want, you can watch that video once again for this for the orientation of the curve. Now next thing is, in our previous class we discussed that whenever we have a point of zero shear, we must always calculate the value of bending moment at that point. So we have a point of zero shear here. We will draw another guideline here and we will calculate the value of bending moment corresponding to this point. Now this time the situation is symmetrical. 30 is the ordinate on this side and 30 is the ordinate on this side. So location of this point is not a problem. These are symmetrical triangle, 2 meter on this side and 2 meter on this side, because the total horizontal distance is 4 meter for this part. So if this point is at the center of portion BC, then this part is 2 meters, and this part we already know is equal to 2 meter. So this location of this point with respect to the extreme end A is 4 meter. It means that we need to consider the value of bending moment for portion BC, and we will plug in x equal to 4 meter in that equation. So here I have done that. Moment for portion BC, and we have calculated the value of moment for x equal to 4 meter. And if we plug in x equal to 4 meter in this equation, we get moment is equal to 0. So the value of bending moment for this point is 0. So it means that these 230 will not be joined like directly, rather we have another point present here, and this 30 will be joined with this 0 with a second degree line, because the degree of the equation is second. And again, for the slope of bending moment diagram, we look at the magnitude of the shear force. Magnitude of shear force is decreasing in this direction, so the slope of bending moment diagram should also be decreasing. And when we move further, for this part, the magnitude of shear force is increasing, which means that the slope of bending moment diagram should also be increasing, and both these curves will be second degree curves. So we reach this 30, and for the last part we need to know how much is the value here. So we have already calculated the value of bending moment at point D is equal to 0, and the equation of bending moment is second degree for this part as well. So we will join this point 30 with 0 through a second degree line, and as the magnitude of the shear force is decreasing, so the slope of bending moment diagram should also be decreasing, and that will complete the bending moment diagram. And in this case we can see that entire bending moment diagram is positive. So it means that the entire elastic curve of this beam will be sagging. So if we come to this diagram, I have to draw the the elastic curve on the beam. This is the center line of the beam, and these are the point loads. We can assume these point loads just like the support reactions, and our elastic curve will pass through these points. The intermediate part of the beam will sag down, and for the remaining part we will just continue the same trend on both the sides, and this will complete the elastic curve for this diagram. And this also completes our discussion for this problem. We have completely shown the shear force diagram, bending moment diagram, and elastic curve of this beam. So we will just stop our recording here. Thank you very much.